Good afternoon. We resume the lecture today again on this series of lectures on Six Sigma. The theme that we are discussing presently are design of experiments. This is a process that is used many times when theoretical knowledge is not sufficiently advanced. It's not advanced yet to the point when you can write down the equations that describe the behavior of the system. Just to kind of remind you where we are coming from, recall this picture that I showed you a long time back. It had the theme again here was the quest of mankind for control of various systems around us. We have on one hand systems such as the weather system or economy or psychology. These are systems where we cannot even list the causes that produce the effect. We can only observe the effect for most part. At the other extreme, we've got the digital watch, for example, where theory has progressed to the point when we can write down the exact equations that basically describe the functioning of my digital watch. Here's an example. The theoretical knowledge has advanced to the point here where I can write down the exact equations that describe the behavior of this watch. In between, of course, are all these other systems. There is medicine, there is chemistry, there is physics, there is engineering, and so on and so forth. Here, of course, we are certainly not at the stage when we can write all the equations, but we are trying to use experiments to move to the right, to slowly move to the right. There was a point, of course, when even electronics was experimental. The theory got built much later as we picked up more and more better and better understanding of what was going on in the real system. So we started at the left extreme, which is like a system like the weather or psychology or economy, when we could not even list the factors. We got to the point when we could at least list out the factors, we could draw the cause and effect diagram. And then we used techniques, various experimental techniques, empirical techniques, to try to sort of develop knowledge that would then gradually move us toward equations that would help us design systems that have predictable behavior, that we can predict. In today's context, of course, we are going to be discussing this technique called DOE, design of experiments. And in particular, I'm going to be focusing today on the calculation procedures that are involved in DOE. When you conduct DOE, you collect data. You collect data in a controlled manner. Now, what do you do with the data? Our goal basically is to try to understand what are the effects, what are the different effects of the different factors that are impacting the system. That's like something we'd like to know. We'd also like to know, is that effect significant when we compare that to noise? And also if there is interaction between the effect of two factors, two or three factors that might be affecting this. So basically, an experiment is a test of a series or a series of tests, and basically these are used widely in engineering and natural sciences and also physical sciences. What we're really trying to do is we're trying to characterize the process and we are trying to achieve optimization of some sort. We might be evaluating material properties of things, or we might be designing a new product, for example, or conducting some sort of developments. And in fact, it turns out that all experiments, they are designed basically in such a way that some experiments turn out to be well designed, whereas some others turn out to be poorly designed. The result is this: with some experiments you can calculate, you can go on further, and you can convert the data into information that you are able to do with certain types of experiments. These are well designed experiments. There are other experiments where this is not possible, that actually indicate some problem with the design of the experiment. That is the manner in which you've manipulated the system and you've collected some response data. Let's see how we do it. The theoretical and mechanistic models, these are models which are based on theory. Then, of course, you've got empirical models. There are, like I said before, there are some systems that we understand very well. We understand their functionings very well, and we can write down their equations either from thermodynamics or electronic circuits or queuing equations and so on and so forth. We can describe the behavior of these systems in an exact theoretical manner that we are able to do. Then there are other systems which are really complicated, and these also involve a lot of noise. And for such systems, for us to understand how they behave, we have to conduct experiments. And the kind of experiments we'd like to conduct, and these experiments are going to be the most effective ones, are the ones that are planned by DOE, design of experiments. So in fact, if you're trying to approach data gathering or knowledge acquisition through experiments, the best way to go there is to use the DOE path. What are some of the examples? There are some examples where you can use theoretical models. For example, project scheduling constrained by resources. You can construct a mathematical programming model for it. This is something we could probably do. When we are looking at the RSSI system, this is a system that helps us locate determine the location of vehicles. This is also possible with a theoretical model. Many times process optimization can be done by applying calculus or other search methods. There again, a theoretical model is available and you can actually go ahead and do it. And of course, in all these areas, science has advanced to the point, science and engineering both have advanced to the point when we can write down the basic equations that describe the behavior of the system. This, of course, is not possible with all systems. An example is engineering systems. Many engineering systems are such we can perhaps list the controllable factors, and we find there are a lot of uncontrollable factors that cannot really enter our equations. Then there are some inputs that the user or the driver or basically the person interested in letting the process operate or perform, he provides some inputs, and then of course we observe the output. These are typically what most engineering systems comprise. What of course we have to do is we have to see how this particular system behaves. Without really having that understanding, we would not be able to control the output of the system, and the system by itself would just be standing alone and we won't really have much use of it. What we'd like to be able to do is we'd like to be able to set up an experimental setup where we control the inputs in a manner where we understand what factors are, what treatment levels are. These are the settings at which these different factors are set. Then of course which factors are fixed and which factors are going to be randomly fluctuating when the experiment is conducted. Then of course the output is what we are interested in, so there could be something that we call the response variables. We'd also like to see as the output of the total empirical study process interaction between factor effect. This is something we'd also like to be able to understand, and also would like to definitely understand the effect of the main factors, the prime actors in the process, the different main factors such as temperature, pressure, concentration. These are the factors that vary in the system, and these are the ones that require some sort of adjustment in order for us to optimize the system and get the performance come out in a manner that's optimal for us. There are certain principles we apply when we use DOE. For example, replication is a process that is used whenever we are replicating the same trial again and again, several times. This is because no matter what system you are looking at, like the system that I showed you, there are some factors which are controllable, but there are many factors that are uncontrollable. Now, the ones that are uncontrollable, those I am not setting, and therefore I do not know when they are on or when they are off, or to what degree they have changed during the experiment and so on. That is really not known because these factors are uncontrollable and many are actually unknown. In a situation like this, the output is going to be noisy. What we'd like to be able to do is, we'd like to fix the settings of the control factors at a certain design setting, and then would like to repeat the same trial several times so that on the average, the effect of the uncontrollable factors would get neutralized by the averaging effect. This is something that we'd like to be able to do. So that is why we use replication. We also sometimes use this principle called randomization, which is like, let's say you're running an experiment, you're running a chemical process, and this experiment is being conducted in a situation, in an environment where the environmental temperature changes from morning to lunchtime to evening and so on. Now, in the morning, of course, temperatures are cool, so you may run the experiments. If you run experiments in the morning, and if you're not controlling the temperature externally, then of course the experiment is going to be subjected to this morning ambient temperature, which is going to be cool. Then around 2 o'clock, which is like about just past lunchtime perhaps, temperature heats up and the weather gets warm and so on and so forth. If you run your trials at that point, perhaps the response would be different because now the external environment, which is the uncontrollable factor, has changed from being cool to warm. Then in the evening, of course, again temperatures cool down. And again, if you run some experiments at lunchtime, when ambient temperature is warm, and then you run it again in the evening, there would be a difference. If you are trying to experiment if you're trying to run your experiments in these three settings, for example, there should not be an order. There should not be this sort of thing should be randomized. So if you've got experimental trials, you should randomize their conduct, the time of their conducting between morning, lunchtime, and evening. And one should not really have, for example, certain experiments run only in the morning, and process settings change, but those experiments are run only at 2 o'clock. Then again, you run the same trials with some other settings of the process factors in the evening. If we do this, there will be some effect of the environment also. But if the environmental sequencing, if it is randomized, then of course the effect of such external factor is going to be then more or less neutralized. So this is the idea of randomizing. Then there are certain other principles also utilized in conducting experiments. These are called blocking. And blocking is a way when there may be a factor that might be impacting your process, but you are interested in neutralizing that effect. So you construct blocks. And this procedure was invented when Ronald Fisher was trying basically to come up with schemes or methods or identify the effect of various factors such as fertilizer, water, sunshine, soil condition, and so on, and seed quality on yield from farms. There he used blocks because he could not really take the same piece of land and run all these different trials and different sequences. He did that by dividing up the total land into blocks, and then he randomized the allocation of the experimental treatments, those he randomized over this. So this is called blocking. Blocking basically does away with any effect that might be there because of that other factor, which is not part of my experiment, but it is something that could also impact my outcome of the experiment. That's why blocking is there. Now let's take a look at different types of setups that we could utilize in experiments. Now, as I mentioned to you, experiments are done by controlling certain factors which we call the experimental factors. And these are also the control factors. We change their settings at will. We follow a certain scheme in changing the settings of these factors. So there are going to be obviously many different factors, and if you do a little cause and effect diagram, you'll find that the main stem of the fishbone that goes horizontally. Then you've got some factors that are affecting this fishbone, basically coming, and these are going to be the design factors. These are the ones that you'll be manipulating. Then there are a whole lot of other factors which are like random factors or noise factors or nuisance factors. These are also going to be impacting your experiment. So basically, the total process would be under the control of part your design variables and part these noise variables. They are both of these sets they are going to be impacting on this thing. So this is something you've got to remember. When we design an experiment, when I design the scheme or the plan to conduct experiments, you've got to be mindful of the fact that the design variables we are going to control, and basically the noise factors nature is going to control. And what we have to do is we have to somehow neutralize the effect of noise, or have a data analysis scheme that can still help me get basically reliable results by looking at the output in a special way so that I neutralize the effect of the noise variables. This is something that will be done when we get into this phase of data analysis. Now, design factors, they may be allowed to vary randomly, or they may be held constant, or they may be allowed to vary according to some plans. That also is possible. So either these may vary randomly, or they may vary according to a particular matrix, or they may be held constant. That is our choice. That is basically the experimental plan. Noise factors may be controllable or may be uncontrollable, but all of these, they are called basically noise factors. And they are the ones, they are factors, of course, they are impacting the system, but we are not terribly interested in looking at the effect of noise. That we are not interested in. Rather, would like to find out whatever the effect is of the design factors so that we can optimize the process. This is what we'd like to be able to do. So what are we talking about? When we talk about design factors, we talk of treatments and levels. Treatments are, for example, they are the different settings at which I could conduct the experiment. There is some process factor which is going to be varying, and I will be able to vary them. This process factor, for example, if it is temperature, I could set temperature at 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius. So there are 4 treatments now: 10, 20, 30, 44 settings possible for temperature. For pressure, I could have two settings. I could have 10 psi and 20 psi. Those are going to be my two settings. So I've got two treatment levels for pressure, and I've got four treatment levels for temperature. When I conduct the experiment, of course, I combine the two. In the full factorial situation, I'll be combining every pair. I'll be basically running the experiments under every pair possible with a pressure setting and a temperature setting. This is what I'll be doing. So it will be 2 times 4. That would be the number of experiments that I'll be running. That will be like 8 trials. But there are, of course, this is a full factorial design. There are other designs which do not require you to run all 8 experiments. And of course, they do not also produce the same amount of information. The full factorial experiment will always produce the maximum amount of information, not only about the main factors, but also about interaction between the factors, factor effect. The partial factorial design, when you choose not to run 8 trials, but perhaps only 4 trials. These are special designs, special matrices that you use to guide your experiment. And these matrices are such, they require fewer trials, but they are clearly not as revealing as the full factorial experiments. We'll see that in a couple of minutes. And of course, when the factors are discussed, when experimental factors are discussed, there are situations when I can fix the settings of these different factors, the factor levels, at certain fixed levels. These are going to be fixed factor experiments. Then, of course, it's also possible that I run my experiment by letting the experimental factor vary randomly, and we look at the impact. These settings are chosen randomly in the randomly chosen experiments, factor guidance. And if the factor levels are randomly selected from a population, the effect is also going to be variable, and the data analysis methods are going to be different from the one where I've got fixed levels. In the fixed level case, I'm going to be showing you both of these. In fact, I'll be focusing mostly on the fixed level experiments, because most practical experiments, they are of the fixed nature, fixed treatment level type. But there are situations when we might use randomly selected settings of these different process factors. That also we could do. Now, what about the response variable? The response variable is something that you measure, and it's quite possible you'd probably measure more than one response variable. Because you're running the experiment, if you can observe multiple things coming out of the same trials, go ahead and do it, because it will reveal more out of the experiments. As far as effects are concerned, as far as factor effects on those responses are concerned, there are two types in which we have a lot of interest. The first is the main effect, and these are the effect of the individual factors, such as pressure, temperature, concentration, and so on. Then, of course, there are other effects which are called interaction effect. These are perhaps the interaction between pressure, between the effect of pressure and also the effect of temperature. Perhaps there is some interaction between the two. And this is what brings in complexity when you look at the response, when you look at the total response of a process. Many times the total response is the composite effect of main effects, which could be as many main factors that you have, as many experimental factors you have, then some complex interaction contributions also that might be there. We'll do some calculations. We'll try to see for the particular system chosen, are main effects present there, and what is their extent, and are interaction effects present there, and what is their extent. We'll see that as we get into it. So the basic principles, just to recap again, we have the idea of randomizing, which is like running trials in an experiment in a random order, so that the factors that you're not controlling, they are not able to affect the experiments, the trials in any systematic way. And of course, many times we'd also like to utilize the effect of the help of random numbers. This is probably used. This is used quite often to try to basically sequence the trials that you've got. So you might run the first trial first, then you might write the 6th trial, then you write the 4th trial, then you write the 3rd trial, and so on. You're randomizing the sequence you'd be running your trials. This is being done primarily, like I said before, in order to neutralize the effect of any factor that you are not controlling, but you want a full nature. Replication is something that we also would be interested in when we're conducting an experiment, and basically the more you replicate, the truer you are going to be to closer to the true response, because you're looking at then with replications you end up finding the average response. That should be looking at. Then of course there is the effect of blocking, which is to try to isolate controllable noise factors. And if you're able to block them, then you neutralize basically the effect of these nuisance factors, and you're able to basically cancel out their effect of each other on the real process itself. That also is quite possible. What sort of strategies people use? The design of experiments method, of course, is the most sophisticated method, statistically designed experiments. Then, of course, there are best guess experiments. I'll give you some examples of this. Then there are experiments that are like one factor at a time. And of course, the best experiments are these statistically designed multi-factor experiments. Let's try to take a look at what these are. The factorial experiment, and I'm going to be giving you an example. And this example comes from the game of golf. And when you're playing golf, your score, of course, the idea is to try to keep your score low. Hit the ball as few times as possible to complete all the 18 holes. Complete walking through the full course and in complete sinking your ball in each of the 18 holes. The fewest number of strikes that you make in doing so, that becomes your score. And the person who is able to do this in the shortest number of trials, he becomes the winner in a golf game. What are some of the variables? What are the different factors that might be affecting your score? The type of the driver. The driver is that hockey-like stick. It's got that head there at the end, and you've got this long stick there, and you bash the ball, you bang the ball, or you putt it, or do whatever. You're doing that with the help of this driver. Various types of drivers are available, and these are heavy, they are round, they've got brass face, they've got composites, and all kinds of things are there. Then, of course, the length of the bar, that can also change. There are various types of drivers available, and they have different names also. So, even if you're looking at only the driver, the real stick that you use to hit the ball straight off the tee to get your first shot. The first shot is usually a very long shot. I'd like to get a driver that actually hits accurately and also hits fast and far. This is what I'd like to be able to do. So there may be some choices there. There may be a special driver, or there may be a regular driver. So there are two types of possibilities. Let's say we are trying to optimize the choice of driver, the type of ball we are going to be using. Are we going to be walking around when we play the game of golf? Are we going to be riding a cart? What kind of beverage we'll be drinking when we basically have the need to drink something? We could either be drinking beer, or we could be drinking water, or perhaps we could drink nothing. That also is possible. The time of round, which could be morning, afternoon, evening, whenever it is. What is the weather like? That might also affect your score. And the kind of spike you are using, and so on and so forth. There are many different factors that can impact your total score, total golf score. Let's say we are conducting an experiment, and we are going to be doing a very simple experiment. And we are saying we've got a choice of two types of drivers. One is the ordinary driver, and the other is the special driver. So I'm just going to be calling them type O driver and type R driver. These are the two types of drivers we have, two types of sticks we have to bash the ball. As far as the ball is concerned, there is the regular ball, and this is called the ballata Italian ball. Or there is the T-type ball. This is a special ball which is marketed by some particular supermarkets. We've got two types of balls also that are available. So what are the two choices? I have basically two drivers with which I can play, with which I can hit, and of course I've got two types of balls that I can use in my play. So 2 times 2, there are 4 possibilities. There are now 4 possibilities. You see then that this actually gives me 2 times 2 or 4 different ways in which I could really play this game. And those are shown here. If you look at the matrix here, these are these 2 by 2, and therefore these 4 possibilities. The first one is going to be type O ball, type O driver and type B ball. So this is O type driver and B type ball. And this one is the R type driver and again B type ball. This is like another possibility. Then of course O type driver and T type ball. And of course this one is the last combination possible, which is like T type ball and R type driver. So I've got OB, and I've got RB, I've got OT, and I've got RT. These are the 4 different ways I could play this game. And borrowing, something that we mentioned earlier, we should not just play one round of game with these 4 different combinations. We should play multiple trials, because there may be these other factors that I'm not including in my game. So let's actually do this. Let's play multiple replicates of the same game. So we'll play the same game multiple number of times. Let's say we play it, perhaps if we have enough money, 4 times each. So we'll be playing the BO combination 4 times, we'll be playing the BR combination 4 times, we'll be playing the TO combination 4 times, we'll be playing the TR combination 4 times. After that, of course, we gather some data and we record the data. And from this, we are going to be working out the effect of the driver, the main effect of the driver. This is something we're going to be working out. So we'll find out if going from O to R, if this reduces our score. It could reduce or it could increase. We don't know that yet. And of course, also when it comes to changing the ball type, in using ball type B versus ball type T, what happens to the main effect of it? I mean, do I end up with a smaller number when I play with ball type T as opposed to playing with ball type B? That's also something we'd like to find out. What we now do is we'll take a look at the results of this game. Let's say I've done that, and in this case, of course, I show you 2 trials only. I show you the effect of 2 trials. So look at the top. This is where, look at the top diagram there. This is where I've recorded my 2 rounds. Basically, I said earlier that we'll be playing 4 rounds at each setting. Let's say I did not have enough money, so I had enough money to be able to play 4 rounds once and then 4 rounds again. This is all I was able to play. I've recorded my scores here. So and I'm going to be writing them down. So I have here, for example, I have for the BO combination, my scores are going to be 88 and 90. For the BR combination, my scores are 93 and 91. And for the TO combination, my scores are 88 and 91. And for my basically TR combination, my scores are going to be 92 and 94. This is the data that I calculated, data that I recorded. Now, of course, I have to do my calculation because I have to find the effect of, for example, type B ball, type T ball. I have to find the effect of using the O driver as opposed to using the R driver. We have to find that. Basically, what we would like to know is, we'd just like to know, is there an effect due to change, my changing the driver with which I hit the ball? Is there an impact on my score if I change the driver from the O-type driver, from being the O-type driver to an R-type driver? This is one of the things I would like to find out. The other thing I would also like to find out is, when I use ball type B versus ball type T, is there an impact on my average score? This is like something I would like to be able to work out. I've already got my experimental data, which is shown here. This is the experimental data that I've gathered. I've run the 2 experiments, and I've done it in a way when I've randomized the trials. So perhaps my randomized trial was, if I just put down the sequence here, perhaps I played this one first, then I played this one, 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 and I'm left with this one. That's what I played the last. As far as 1, 2, 3, 4 are concerned, I have randomized them. So hopefully the effect of all the other factors is going to be averaged out because of my randomizing. Now what we'd like to be able to do is, we'd like to find the effect of going from type O driver to type R driver. Let's see how we find that out. What we have to do is, I again go back to the picture here and I show you. What I do is, I take an average. I take an average here. First of all, I have to find the average of 88 and 90. That's something that will be the average score there. I do the same averaging here. I do the same averaging here. I do the same averaging here. This, of course, is not going to be terribly difficult. This is going to be 89. This is going to be 92. This is going to be 93. And this is going to be basically 89.5. Those are going to be my averages. So let me write down my averages, and my averages are going to be, I'm just going to put down the averages here. Average score is going to be here, it's going to be 89. It is going to be 92. It is going to be 89.5. And this is going to be 93. These are the averages. The utility of these averages is that this has neutralized then the effect of the factors that I did not control when I was playing my game. I put all of those as factors that were other than the driver and the ball. This is what I did. From this, of course, we are supposed to find the effect of the changing balls or changing the driver. Let's see how we do that. What I do is, I find the average of two quantities, and those two quantities are going to be the following. I average out these two, and I average out these two. Let's try to do that, and let's try to do that precisely. I'll be using a calculator, so I'll just put that here, and I've got essentially 88 plus 90 divided by 2. That's 89. That's already there, so that is confirmed. Now let me average out this one, these two. I have 89 plus 92 divided by 2. That's 90.5. So that number is going to be 90.5. So I have 90.5. And what is common between these two? B. B is common. So this is going to be the effect of B. I'm going to be telling you a little bit more about this in a couple of minutes. Let's also average out these two quantities. I've got 89.5, 89.5 plus 93 divided by 2. That's 91.25. And when I'm doing this, what is common between these two is T. Now remember, my column here, this column was for balls. And this column here was for driver. And what I've done here is I've found really the average effect of playing with ball type B and the average score of playing with ball type T. So I could quite easily, at this point, produce a plot. Now what would that plot be like? I could just draw the plot here. I'd first draw the axis. And I'd start at 95, and then I'll have, or let's make it 85 because it's quite low, 90, 95. And let's put on this side the two ball types, and those are going to be my B and T. B and T. What do I see now? I see the score of B to be 90.5. That's about here somewhere. Score of T is going to be 91.25. That's going to be somewhere here. If I join them, there's a slight rise. As you can see, there is a slight rise from 90 to 91.25. That slight rise is because of the change that I made in going from ball type B to ball type 2. This is the effect. In fact, if you look at the number carefully, you'll find this delta. This delta is due to ball change. That is the effect of basically changing your ball. Let's do the same calculation using the driver. So for that, what we have to do is we have to average something different. Let's see what we average. We write down here the average of type O first. So that's going to be, I put down here the average of O type first. So that's going to be 89 plus 89.5. And I'll work out the average of it. That's going to be 89.25. So I can directly write here the effect of O type driver is 89.25 O type driver. Just like I have B type ball giving me 90.5. For O type driver, I end up with a score of 89.25 on the average. Let's look at the other one. And the other one is going to be R type driver, and that's going to be basically the average of 92 and 93. That's going to be 92.5. That's going to be the effect of the R type driver. So here again, the change that took place when I change my driver from O to R is going to be an increase in score. And this I can again write, I can plot it again. Like I did my plotting before. I can plot like this. I'll have some quantities there. Start with 85, 90, 95. This always is, this side, the y-axis is always my golf score. So it's going to be a score here. Score is going to be on this side. And what do I plot on this side? Let's try that. Let's try to write that. I have 89.25. That's going to be, let's first put down what is it that we are plotting. We'll plot type A. Type O is here and type R is here. And these are what? These are driver types. I have O type driver and R type driver. For O, the score is 89.25. That's the average score. That's somewhere here. And for R, the average score is 92.5. That's going to be somewhere up here. If I join them, that shows me an increase. And again, as we did before, let's show this effect. This is also a main effect. This is also a delta that is due to driver. This change is due to the driver changing from O to R. This is the change in score. This is the change in score. So both this is the main effect. I can just write it main. This is also a main effect. Main effect always is the effect of a single factor. Main here and main here. So I've got a main effect calculated there and a main effect calculated there. Now what about interaction? Interaction becomes a little more complicated to evaluate. And for that, what we do is we'd average out two quantities. We'd average out 88, 90, 92, 94, which is like 89 and 93. If you average these two out, I can actually get an interaction factor. I will say and I'm just going to be plotting that directly. So let me just get my scale here first. I'm going to be plotting this time the interaction between the two. So I'm going to be my scale here, interaction low and high, and I'll just call it interaction. And this interaction is going to be now between ball and driver. Low and high. And let's see how you calculate that out. And of course, my scale is marked at 85, 90, 95. That's my score. Let's try to see if we could get my interaction plots done. I'll just make sure the reading is okay. I have the low level is going to be the middle point. So that's going to be the average of 92 and 89.5. And that's going to be very close to, if you really look at it, I could just use the calculator to do that. 92 plus 89.5 divided by 2. That's 90.75. 90.75 is the low level. That's about here somewhere. And let's do the other one. That's like the average between 89 and 93. That's actually 91. So I'm going to be putting that right about here. 91. Notice here, it looks like there's almost no interaction. This is the interaction one. So let's at least give it a title. This is interaction. What have we done? Let's try to summarize what we've done. We ran some experiments, and our experiments were run using, in this particular case, different types of balls, 2 different types of balls and 2 different types of drivers. We ran those trials and we ended up the data here. Where is the data? Let's try to put that within a red sort of zone. My experimental data are right here. That's where my data is. This is my experimental data. And if I just shift the thing a little bit, you'll be able to see I wrote data there. When I have my data there, the only thing I have to do is I have to remember under what settings I obtained those things. What are these 2 numbers? These are 2 replicates of experiments run. That is like my game played under the same settings. I was using ball type B and driver type O. And I played 2 rounds and the average turned out to be 89. I ran this other trial. This is like the other game I played. Another game I played. Ball type B, driver type R. And the